Alrighty, good morning everybody. Welcome back to Calc 3. Plan for today is we are going to start talking about standard 12s. Kind of make the transition to looking at local extrema. Office hours for the next couple days are at the usual times. This afternoon from 2 to 3, tomorrow morning at 10, tomorrow afternoon at 1. And Wednesday in the hour before class and at 2. As far as homework goes, as I said in the email, Standard 11 quiz is going to be on Friday rather than today. That's because we missed class last Friday. Turns out I came down with a bit of a nasty cold. Feeling a lot better now, though. Yeah, I'm sorry to have to cancel class on you the day before break like that. I don't know how upset you all are at that, but... anyways, like I said in the email, I recorded a video, put it on YouTube, my YouTube channel to make up for that. A little bit of a shorter class. I moved the Standard 11 quiz to Friday to give you all the chance to come ask me about that in office hours. But the Exam 2 is still going to be this Wednesday, where Exam 2 is going to be over every standard we've done so far. Not what we're doing today, but everything before today, including the video from last week. So encourage you to watch that before Wednesday if you haven't. It's going to be similar in format to the first exam. Just going to have one page each for every standard 1 through 11. First exam I wrote with the intention that you could complete the entire exam. This one I did not. Every exam is cumulative in this class, and going forward, I'm going to write the exams with the intention that you don't do every problem. You can try and work your way through 11 problems if you want. I do not recommend it. Write the problems to take about 10 minutes each, so you do the math. Instead, what I encourage you to do is to maybe pick like 6 or potentially 7 standards that you'd like to test over for this Wednesday's exam. And just do those. If you leave a problem blank, just like with the first exam, and that does not affect your grade in any way, just like with the first exam, you are allowed 1 sheet of notes, front and back, whatever you want written on it to help you out. In fact, if you want to take your page for the first exam and just write more, go for it. And I'll let you have that sheet of paper every exam going forward. Any questions or comments before we get started for today? Great. In that case, let's do some math. So, a new packet for y'all, Standard 12. By the way, just to give you a sneak peek, exam on Wednesday, Standard 11 quiz Friday. I'm expecting Standard 12 quiz will be next Monday. I think Friday we'll probably work our way through get through the rest of Standard 12. So, we're kind of entering our third unit in this course, the unit on optimization, where we're sort of looking at how do you take a multivariable function, find where it's biggest and where it's smallest. Yes? Yeah. And in this standard in particular, we're going to focus on the idea of how to find local extrema, how to find local maxes and mins for a multivariable function. Yep. And so, like what we've done recently with a lot of our standards, I'm going to start off class today with sort of a review of Calc 1. What did it mean in Calc 1 to find a local max, a local min? How did the second derivative test work for determining it? And then we'll generalize, kind of in the second half of class today, and in Friday's class, we'll generalize to how do all of these different terms apply to looking at multivariable functions. Specifically, functions going from Rn to R. So to start though, we're going to look just at Calc 1 functions. So there's the scoop. We're going to draw a function on the board. And I want you all to determine where this function has local maxima and where this function has local minima. So this is going to be a function, f of x, going from r to r, where the inputs are x values and the outputs are our y values. And what I would like for you all to do is to take just a minute and see if you can determine at which values of x is this function going to have local maxima, according to your kind of what you remember from Calc 1 as being sort of your intuitive definition of what a local maximum is, a point a point on the graph whose y-coordinate is bigger than all the other y-coordinates close by, and ditto with local maxima. In other words, at which values of x is the y value going to be smaller than all of the other y values close by? So I'll give you a minute to copy this graph down and see if you can determine which values of x you think we're going to have local maxes versus local mins. And then we'll come back together in a minute and see what your thoughts are. Yes? Oh my gosh, there's a joke. Oh my gosh, I don't have a joke. I'll tell you what, work on this while I get a joke and I'll tell you the joke before we talk. Okay. Why was 6 afraid of 7? Is 7 eat 9? But why? Why did 7 eat 9? Because 7 knows the importance of eating 3 squared meals a day. Okay, so now that you've all had a chance to sort of look at this graph, anybody tell me a value of x at which we're going to have some sort of either a local max or a local min happening? Bob?
-3 is one local maximum.
So you think we have a local max at x equals -3?
Yeah.
Why is that?
It's where the graph switches from going upwards to going down.
Ooh, yeah, it's going up to down, meaning the y value at this point is going to be bigger than all the y values of all the points close by. Yeah, I can get behind that. To me, it looks like at x equals -3, we have it's not just going to be a local maximum. What else is going to be happening at -3 that's a stronger condition?
I forget the term, but something like a global maximum, essentially.
Yeah, a global maximum, or absolute maximum. I prefer the term absolute, but global works just as well. In fact, at -3, we have the largest y value on the entire graph. There's no point on our graph with a larger y coordinate than at -3. So that's going to tell us at -3 we'll have both a local and an absolute maximum. Absolute maxes we'll talk about in the next standard, by the way. Any other points that you all found that at which we had a max or a min? Mm-hmm. Nope.
X equals 0 is a local minimum.
Why is that?
Because that's where it is switching from going down to going up.
Yeah, the y coordinate there is small. Well, let's try and graph this a little more accurately. But yeah, at this point, our y coordinate is smaller than all the points nearby. Or, as you said, the first derivative is going from negative to positive. It's going from decreasing to increasing. Are we going to have an absolute minimum at x equals 0?
No, because at both ends of the graph, it's going further down.
Yeah, if we were to go far enough out to the left or to the right, we're going to be getting points with whose y-coordinates are less than at 0. But at x equals 0, we still have a point where the y-coordinate is smaller than the points that are nearby. So it's going to be a local minimum, but not an absolute minimum. Any others? All right. Who do I want to pick on? Lindsay. Any other extrema on this graph?
There's also a local max
At x equals 2, so right here? Is that going to be an absolute maximum? I would agree. It's a local max, in that the y value at this point is bigger than all the ones nearby, but it's not absolute because out here at -3, the y-coordinate's going to be even bigger. Okay. So at x equals 2, we are going to have a local maximum. By the way, plural of maximum is not maximums, it is maxima. Ditto with minimum. That's a Latin lesson for you. And finally, any other points that you all would want to describe as being extrema? Local max or local min? How about at x equals 3? Is that going to be a location of a max or a min? Lauren?
No, because like to the west, it's like decreasing and to the right also.
Yeah, I would say the y-coordinate at this point is bigger than the y-coordinates of the points a little bit to the right, but smaller than the y-coordinates of the points a little bit to the left. As you say, it's going from decreasing to decreasing. Just so happens we have a point where the derivative's undefined, but that's still going to be a point where we don't have a max or a min because the y-coordinates are not bigger than all the points nearby, and it's also not going to be smaller than all the nearby points. And so, in fact, these are going to be all of our extrema. Extrema, by the way, plural of extremum, is just going to be the plural, or not the plural, the general form of max or min. So if you ever hear me say extrema of this function, I mean maxes and mins. Any questions or comments? So what's going on with the first derivative of the function with f prime at x equals -3 and at x equals 0? Say about the derivative of our function there. Yeah?
The derivative captures the slope of this graph.
Mm-hmm.
So at x equals -3, the derivative will be, before it will be positive because it's an increasing graph, and after it will be a negative value because it's a decreasing graph.
And at -3 itself?
It'll be 0.
Yeah, we have a slope, our function, if we drew a tangent line at both these 2 points, we would end up with a slope of 0. Our tangent lines have a slope of 0, meaning they're just horizontal lines. How about at our other extremum, at x equals 2? What appears to be going on with the derivative at x equals 2 here? Luke?
Isn't it undefined? Because technically you can have there are multiple values that would fit as a tangent line, and therefore it's undefined.
Yeah, our slope from the left is different from our slope on the right. And so there's not going to be a single value at x equals 3, or at x equals 2, excuse me, that we could say is going to be equal to the slope of the function at that point. Alternatively, it's pointy there, and pointy things are bad. Pointy things are sharp and hurt and prick your finger. So it's going to turn out to be the case, you might remember from Calc 1, that anytime your function has a local max or a local min like this, one of these two things is going to happen. Either your slope f prime is going to be 0, or f prime will be undefined. And the points in your graph at which that happens are going to be called critical points. So, Calc 1 probably saw this term where f of x has a critical point at a value x equals a if a is in the domain of f, meaning at x equals a you have an actual point, f of a exists, and either f prime of a is equal to 0 or f prime of a does not exist. So any point in our graph, so for instance, in this graph, I think we can say we'll have critical points at x equals, let's see, -3, 0, 2, and +3 are all going to be values here that are in the domain of our function, meaning at any one of these 4 points, we could plug it x into the function and get an output, unlike at, say, x equals -2, where f of -2 does not exist. All 4 of these are going to be points that are in the domain and that also are either going to have a first derivative, f prime is going to either be 0 or undefined at each of these 4 points. It'll be 0 at x equals 0 and -3, and it'll fail to exist at x equals 2 and 3 because the slopes from the left at those 2 points are going to be different from the slopes coming from the right. And the theorem we have that's going to relate critical points to local maxes and mins, you may have seen this theorem called something else like Fermat's theorem before. This theorem kind of goes by a few different names. I'm going to call it the extreme value theorem part 1, but if you want to call this theorem something else because you've seen it called something different before, go right ahead. The extreme value theorem this is the Calc 1 version, because we're going to see a Calc 3 version later in class. It's going to tell us that if f is continuous at a point A, in your packet it's going to say continuous over an interval. Scratch that out and just write continuous at A. If f is continuous at A, then f can only possibly have local maxima or minima at A if f has a critical point at A. In other words, we can generally say that if a function f of x is continuous, and if it happens to have a local max or a local min at some point on our function, then it's going to have to be the case that f has to have a critical point there. Meaning at any point at which we have a local max or a local min, the slope is either going to have to be 0 or undefined. It's kind of a classic Calc 1 result. So anytime you have a local max or min, you're going to have a critical point. Is the reverse going to be true? Meaning, if we know that our function has a critical point somewhere, do we necessarily have to have a local max or min? Or is it possible to have a critical point that isn't a max or min? Sarah, you look like you have a thought.
I'm pretty sure there are some graphs that the slope almost like just gets to 0 and then immediately like goes back to something like this.
Oh, like a weird sort of like cusp or corner behavior? Yeah, can you think of an example of a function where that sort of thing might happen? Where it's possible to have a critical point but not a
I can't think of one on the top of my head.
Luke, you want to help her out?
X equals 3 on that graph.
Yeah, I think this is actually an example right here of the sort of thing you were describing, Sarah, where it sort of looks like the slope goes to 0 on one side at least, but then on the other side it kind of goes down and does something else. So at x equals 3, we actually have an example in this graph of a function where we have a critical point where f prime of 3 does not exist, but it's also not an extrema, meaning we don't have a local max or a local min at this point. Another example of something like that, where f prime does exist and equals 0, but we don't have a max or min, would be something like f of x equals x cubed. Where if we look at the graph, we're going to get something like this. At x equals 0, we can actually see that f prime of x equals 3x squared. So at x equals 0, we will have a critical point, but it won't be a critical point, but it'll be a critical point where we don't have a max or min. Because if we look at this graph, if we go to the right a little bit, our function is going to be getting bigger. That's spooky. Whereas if we go to the left a little bit, our y values are going to be getting smaller. So this would be an example where we have a critical point where f prime is 0, but we still do not have a max or a min. So max or min means you have to have a critical point, but the vice versa is not necessarily true. If you have a critical point, it's possible that you have a max or min. It's also possible that you do not. Any questions or comments so far? So there's actually a couple theorems in Calc 1 that we can actually use to determine whether, once we have a critical point in our function, whether or not the function is going to have a local max or a local min. The first derivative test and the second derivative test. The first derivative test is the one that says if f prime goes from positive to negative, you have a local max. If f prime goes from negative to positive, you have a local min. The one I want to focus on as sort of a bit of review is the second derivative test, which is going to be the one that is going to be generalizable to what we're going to be doing when we get to the Calc 3 part of looking at local extrema. What the second derivative test is going to tell us is it's going to be a way to tell, looking at f double prime, using the sign of f double prime, if f double prime is positive, negative, or 0, you can look at a critical point and check if your function has a local max or a local min. And the way it works is we can say if f has a critical point at x equals a, such that, first of all, let's assume f double prime of a is negative. And so if f double prime is negative, that means we have a concave down function, where as we go from left to right, our slopes are getting less and less positive and more negative. If we have a sort of function that behaves like this, where f double prime is negative, meaning as we go from left to right, f prime is becoming less and less positive, and eventually more and more negative, what type of local extremum are we going to have at a point like that, where our first we have a critical point, and f double prime is negative? Is that going to give us a local max or a local min? Holly. It's going to give us a local max. A point like this, it's going to give us a local max on our graph. So if f has a critical point, and if f double prime of a is negative, then f has a local maximum at x equals a. And similarly, if we have a critical point where our second derivative is positive, meaning as we go from left to right, our slopes are going to become less and less negative, and eventually more and more positive, if we have a critical point where our function is concave up, where the second derivative is positive, then f is going to have a local minimum at x equals a. So what about the third case, where f double prime of a goes, instead of being negative or positive, what happens if f double prime of a is equal to 0? Anybody remember what the second derivative test tells us in the case where both f prime and f double prime are equal to 0? Laurie?
I can forget.
Change your mind? Ah, okay. So what do you think could happen if our second derivative is neither positive nor negative at our critical point? If the second derivative is negative, we have a local max happening. If the second derivative is positive, then we have a local min. Anna? Yeah, it could be. If the second derivative changes sign from positive to negative or negative to positive, which often happens in these scenarios, yeah, we would have an inflection point. But what happens with regards to looking at local maxes and local mins? Are we going to have one? Jim?
No.
It's a trick question. We don't know. It could or it could not. Then the test gives us no info. Meaning we could have a max or a min or a neither at x equals a. Yeah, sorry. That was a bit of a tricky one. Anna, you're absolutely right. We very well could have an inflection point there. But it's possible to have something like f of x equals x cubed, where if we take f double prime of 0, well, f double prime here, if x is 6x, so f double prime is 0. Here's an example where f double prime is 0, and we have neither a max nor a min. But we could also have something like, say, g of x equals x to the 4th, where g double prime of x is 4x cubed is 12x squared, where at 0, our second derivative comes out to 0, and yet we still have a local minimum. So if your second derivative is 0, it could still go any which way. You might have a max or a min, or you might have neither there. In that case, the second derivative test usually just tells you, go try the first derivative test instead. But the moral of the story is that if you know the sign of your second derivative at a critical point, that's going to be a nice way for you to be able to tell, in a lot of cases, if your critical point is the location of a local max or a local min. Let's look at an example where we're given just a function, and our goal is going to be to find all the local extrema of that function. Meaning, here's a formula. Let's see at which values of x we have a local max, and at which values of x we're going to have a local min. So the function we're going to look at is f of x equals x to the 4th minus 8x squared. If we wanted to use the second derivative test to help us find where does this function have a local max or a local min, what do you think would be a good first step?
I think it's derivative.
Cool. All right. X to the 4th becomes 4x cubed, minus 8x squared becomes minus 16x. Neato Dorito. You have its derivative. What do we do with it?
could say that to rule out any where it doesn't exist, say the domain is all real numbers.
Yeah. So it sounds like you want to find critical points.
Yeah.
Yeah. So in other words, Jacob's idea is going to be we're going to start by finding the critical points of this function. Points in the domain where f of x either exists or excuse me, where f prime does not exist or equals 0. Are there any points where f prime does not exist? Will, see you shaking your head? No. F prime is a polynomial, and polynomials are defined everywhere. So there's not going to be any critical points here where f prime turns out to not fail to exist. So Jacob, what do we have to do then if we want to find all our critical points?
Set it equal to 0.
Yeah, all of our critical points are going to be the other type of critical point where f prime is equal to 0. So we need to find all values of x where 4x cubed minus 16x is 0, because those are going to give us our critical points, which are going to be the possible locations of local maxima and local minima. How are we going to find the values of x that are going to make this 0? Any strategies? Bob?
So one of the first things we can do is put it in a form where there is zero columns. One of the first things I would do is divide an x out of every term and get the 4x squared minus 16 in parentheses with an x on the outside.
Okay, so you want to factor 4x cubed minus 16x, it sounds like. So if we do that, we'll get a x times 4x squared minus 16 is going to give us 0. And we can use the technique in math where if we multiply two things to give us 0, then one of the two terms has to be 0. So either x is equal to 0, or 4x squared minus 16 is going to be equal to 0. And if 4x squared minus 16 is 0, that's something I think we can get x squared by itself, where we'll get 4x squared equals 16. We can divide both sides by 4 and get x squared is equal to 4. And if x squared is equal to 4, Olivia, what's that going to tell us that x can be?
Positive or negative 2.
Yeah, x is going to be plus or minus 2. So it's going to turn out to be the case that we have 3 critical points for this function. We have a critical point at negative 2, 0, and at x equals positive 2. So we have 3 critical points, 3 points at which we could potentially have a local max or a local min. How do we check to see if we have a max or a min, or neither at those 3 points? Max? Yeah. Sounds good to me. In other words, let's take f double prime of each of those 3 numbers, and if it comes out, depending on whether f double prime comes out to something positive or negative, that's going to then tell us if we have a local max or a local min. And hopefully f double prime doesn't come out to 0, because then we'll be stuck. So if we do that, we can take f double prime of x. Let's see, if f prime is 4x cubed minus 16x, then f double prime is going to be 12x squared minus 16. We plug in our 3 points. We'll get f double prime of negative 2 is going to be 12 times negative 2 squared minus 16, which will be negative 2 squared is 4 times 12 is 48 minus 16, which is, I don't know, math is hard, but I'm pretty sure that's going to be something positive. If we take f double prime of 0, we're going to get 12 times 0 squared minus 16, which I'm pretty sure is going to be negative. And finally, if we were to take f double prime of positive 2, we'll get the same thing as we did at negative 2, 48 minus 16, which will come out to something positive. So at our 3 critical points, at x equals negative 2 and positive 2, the second derivative came out to something positive. Whereas at x equals 0, our second derivative ended up being negative. So, Jack, what's happening at our 3 critical points then, according to the second derivative test? Where are we going to have a local max versus local min?
X equals negative 2, you'll have a local min. At x equals 0, you'll have a local max. At x equals 2, you'll have a local min.
I like it. Yeah. Since the second derivative is positive at x equals plus or minus 2, we could say at x equals plus or minus 2, f has a local min. And at x equals 0, f has a local max. Is what we found. Because these were our 3 critical points. Those are the only points at which f could potentially have a local max or a local min. Since f double prime came out to something positive at plus or minus 2, the first part of the second derivative, the second part of the second derivative test tells us that f has to have a local minimum at those 2 points. And since f double prime is negative at x equals 0, first part of the theorem is going to tell us that we happen to have a local maximum at that point. And in fact, wake up. We look at a graph of our function. We can actually see, if we were to look at a graph of a function, hey, wake up. So here I went to Desmos, which is a nice tool for graphing functions from R to R. We can actually see that the function has a local maximum at x equals 0 and local minima down here at x equals positive 2 and negative 2. Our graph sort of looks like, I don't know, 2 teeth that are really close together, and if your teeth look like that, you should go see a dentist. Any questions or comments about what we did here? Where we determined whether we had local maxes or mins by finding our critical points, by seeing where is f prime 0 or does not exist, and then we plugged those critical points into the second derivative, tell us whether we had a local max or a local min at them. So I went through this pretty quickly, but I'm assuming you've all seen this before back when Calc 1. And so the rest of today and in Friday's class, we're going to be generalizing how can we do a very similar sort of approach to find local maxima and local minima of a Calc 3 function. Specifically looking at functions going from Rn to R. Projector, I love you. Ugh. So next up, we're going to be on the 3rd page in the packet, where we're going to talk about how do all these terms come out to be similar but slightly different when we're looking at a Calc 3 function. Where here, we're going to assume that we're looking at a function f going from Rn to R. And what we're going to say to start off, we're just going to define what is a local max, what's a local min, what's a critical point. To start off, we're going to say that a function from Rn to R is going to have a critical point at x equals a, where this time, since our function has inputs in Rn, we're not just going to write x equals a like in Calc 1. We have to use the vector notation because our inputs to this function are going to be vectors in Rn. Turns out our function is going to have a critical point at the vector x equals a if the same things in Calc 1 critical points end up happening. Meaning, we first of all need that a is in the domain of f. So, in other words, f of a has to exist. And either one of two things has to happen. The first way to have a critical point, just like in Calc 1, is if the derivative does not exist at a, meaning f of x is not differentiable at a. Or the other thing that happens, which is our derivative comes out to 0. The trick for a multivariable function is when we say the derivative comes out to 0, the derivative of a multivariable function, keep in mind, is going to be a whole matrix of values. All the partial derivatives of f evaluated at a. And so when we say that the derivative comes out to 0, what we really mean is that it's a matrix, all of whom have 0 as their entry. All of whose entries come out to 0. So in other words, if del f del x evaluated at a is 0, del f del y evaluated at a has to come out to 0, etc. Meaning all of the partial derivatives of f evaluated at a need to be 0 in order to have a critical point. Or the other way you can have a critical point is f of x is just not differentiable at a. Meaning if one or more of the partial derivatives are undefined at a or are not continuous there. So critical point means basically the same thing as it did for a Calc 1 function. We just have to kind of update the notation a bit to say, what do we mean when we say the derivative is 0? Means that all the entries in the derivative matrix come out to 0. Local max and local min are going to be basically the same definition as well. We can say that f has a local maximum at a if f of a is greater than or equal to f of x for all values of x that are near a. Meaning any input x that's close to the value a is always going to have that f of x is less than or equal to f of a if there's a local max there. Meaning at all the points close by, the largest output to our function, so this would sort of be the largest z-coordinate of our function, is going to be biggest at your point A, if there's a local max there. And similarly, we can say that f is going to have a local minimum at A if f of A is less than or equal to f of x for all values of x that are near A. Something to think about, though, one way in which this is different is that in Calc 1, when we say all values of x that are near A, we just mean for all x a little bit to the left and a little bit to the right of A. There's only two directions that you can say look at for x that's close to A. For a multivariable function, you have to talk about all the x near A in infinitely many directions. To the left, right, up, down, any directions compared to A, we would have to compare and see that f of A is bigger than all those nearby points or smaller than in the case of a local min. And before we look at an example, one quick theorem I want to give you that's going to work the same way as it did for multivariable functions as it did in Calc 1 is the extreme value theorem. And this will be the Calc 3 version, where the Calc 3 version of the extreme value theorem is going to say that if f is a continuous function with a local extremum, so a local max or min at a, then f must have a critical point at a. So just like in Calc 1, if you have a local max or a local min, then you have to have a critical point. A point in the domain where either f is not differentiable or where the derivative is just a zero matrix, meaning all the partial derivatives come out to zero. If you have a local max or a local min, a critical point is going to happen. And as we'll see, if you have a critical point, though, that's not necessarily going to guarantee you have a local max or a local min, just like it didn't in Calc 1.
What does it mean that f of a in greater than 4 equals to what would it look like?
So let's say we had the constant function f of xy is equal to 2. What would that look like graphically? Is it going to be a plane, a line, a circle, a clown face? Yeah, that's just going to be a flat plane at a height of z equals 2. It goes off forever in the x and y directions, which is technically every single point on this graph is going to be a local max and a local min. Just because every point at any point A on this graph, f of A is going to be exactly equal to f of x for all points close by. So technically, what that means is every single point on your graph is going to be a local max or a local min. It feels really weird. It's the same thing as saying in Calc 1, if we were looking at the function f of x equals 3, which will just be this flat line, every point on this line has a y value that's greater than or equal to every other point. So every point's going to be a local max. And by the same notion, it's going to be a local min. Why do we want this? For more complicated reasons we're going to get to in like a couple standards right now. Basically, it's going to be because later on, especially when we talk about absolute maxima or minima, we want to allow that the same absolute max or minimum value happens at multiple points. And the reason why we're going to need greater than or equal to versus less than or equal to is just to allow for the fact that it could happen at multiple points, as long as it's the same y value. So what I'd like to do now is I want to take a look at a graph of 3 different functions, and I want you all to tell me where does it look like this function has a local max, a local min, or potentially none of the or neither. So specifically, I want to look at the functions. These are all going to be from R2 to R. F of xy equals x cubed plus xy squared plus x squared plus y squared. g of xy equals 1/2 x squared minus y squared. And finally, h of xy equals sine of x times, actually, let's not do it there. Let's do it over to the side. Trying to get it so the projector doesn't block it too much. H of xy equals sine of x times cosine of y. And it's going to be your all's job to tell me what kind of extrema we're looking at for each of these. So let's start off looking at f of xy equals x cubed plus xy squared plus x squared plus y squared. So here is going to be a graph. Whoa. Here's going to be a graph of what this looks like, where we plug in values for x and y, and the output to the function is going to be the z value. My question is going to be, does it look like this function has to have a local max or a local min at any point? Meaning, is there a point in the xy plane where it looks like the z value output is going to be bigger or smaller than all of the other points that are close by to it? Ren, I see you nodding your head.
It looks like there's a local minimum of the origin,
Why is that?
because all the points around it are bigger.
Yeah, I would agree. Looks like we're going to have a local minimum at the origin, because at any point close to the origin, so any point near 0, 0, the z-coordinate is always going to be bigger than what it is at the origin itself. By the way, does it look like we're going to have an absolute minimum at the origin, or just a local minimum?
Just a local.
Yeah, because if we go out, and say the which direction is this? This is the negative x direction, to like x equals -2, we're going to get z values that look much smaller than at the origin. But close to the origin, all the points are going to have slightly bigger z coordinates than they do at 0, 0 exactly. So we're going to say it looks like f has a local minimum at 0, 0, since the z coordinate there is smaller than all of the nearby z coordinates on our graph. So local minimum at the origin, it's going to turn out that this function doesn't have any local maxima. How about our next graph? So our next one is 1/2 x squared minus y squared. Trying to do it, something like that, so you could sort of get it rotating freely. So my question is, does it look like we have any local maxima or local minima on the graph of this one? Jacob?
I think it looks X is 2. I don't think you're rotating it again.
Sure. Sorry, let me rotate a little bit.
Yeah, X is 2 and -2. It looks like there's local max.
Up there?
Yeah.
It's not going to be, only because the graph actually keeps going past
Oh.
this point in the positive x, positive y, negative x, negative y directions. If this was the entire surface, then yes, but technically the graph's going to keep going up this way in this way forever. But if this actually was everything, then you would be right. Katie?
Well, at the origin, I think it's a critical point that was that from some directions is a local min, from some it looks like a local max.
Yeah, it's interesting. It looks like in the x direction, it's sort of looking like a local min. Like meaning the x value at the origin is going to be smaller than all the x values nearby, it looks like. But if we rotate it 90 degrees, it looks like the opposite thing's happening in the y direction at the origin. That in the y direction, it's going to look like we have a max going on at the origin. And so, yeah, I think you're absolutely right, Katie, that it's going to be a minimum in the x direction, a maximum in the y direction. So what would you say overall is happening?
It's not a local max or a local min.
It's neither a max nor a min. Bingo. Because when we talk about a max or a min, we talk about the z value, the output having to be smaller or greater than all of the points nearby. Well, at the origin, the z-coordinate is smaller than some of the points nearby, but bigger than the others. And so we have neither a max nor a min there. But you were right that we do have a critical point there, and that del f, del x, and del f, del y are both going to come out to 0 there. The graph sort of flattens out at the origin. And so, eraser, where are they? Here you go. I'm just going to erase. We're going to have a special type of point called a saddle point at the origin. Where what's going to happen is that we're going to have a point at 0, 0. The function g has a critical point that is neither a local max nor a local min. And we are going to call points like that for a Calc 3 function going from Rn to R, where we have a critical point that's not a max and also not a min, is a saddle point. So why do you think the name's saddle point? What do you think? Why do you think this type of critical point that's neither a max nor a min might be called saddle? Any ideas? Brown?
It looks like a saddle.
Yeah, this is basically a graph of like what a horse saddle might look like. If you wanted to saddle up and ride a horse, probably put something like this on the horse's back for you to sit on. You know, maybe with the edges tapered down a little bit, as it looks like that kind of looks a little bit uncomfortable. But that's basically the shape of what a horse's saddle looks like. It is the sort of point where in one direction you have a min, another direction you have a max. You don't have a local max or a min overall at that point, but you still have a critical point where it flattens out. And so since this is kind of the prototypical example of what a saddle point is, it's kind of the most standard example of critical point that's not a local max or a local min, we're going to call these sorts of points where that happens a saddle point going forward. And finally, let's look at h of xy equals sine of x times cosine of y. What do you think? I'll pick on you, Jacob, because you answered my question earlier. Does it look like it has a local max or a local min?
I think so.
It looks like it has one of each, but you were burned before when I told you could zoom out. Let's zoom out a little bit on this one and see if you still think we have a max and a local min. So I'm going to go from x and y, go from -10 to 10. change our axes as well. And make it do 60 grid lines, so it's a little bit easier. What do you think? We have maxes and mins? How many of each?
And a whole bunch of them.
A whole bunch of them. I'll give you a hint. If we zoomed out more, we would see even more. It's going to turn out to be the case that this function has infinitely many maxes, and local maxes and mins. Anybody think of a Calc 1 function like that? A function from Calc 1 where you have infinitely many values of x at which you have a local max and infinitely many where you have a local min? That?
Sine or cosine function.
Yeah, just the individual pieces of this function. Just f of x equals sine of x or f of x equals cosine of x are similar in that they have infinitely many local maxima and minima. Cosine, for instance, is going to have a maximum at every even multiple of pi and a minimum at every odd multiple of pi. So like f of x equals sine of x cosine x. So it turns out, just like in Calc 1, you can have these sorts of multivariable functions where infinitely many points pop up where you have a local max or a local min. I like how you're a lot more cautious the second time, Jacob. And I didn't zoom out. Any questions or comments? So, finding maximum and minimas off a graph is all well and dandy, but we'd also like to be able to have a way to just look at a formula for a multivariable function and determine whether we have a max or a min or neither at a critical point. And we're actually going to have a generalization of the second derivative test, a way to use the second derivative test to tell us if we have a local max or a min in Calc 3 functions. And we'll do that on Friday. Have a good day, everybody. So on Friday, we'll look at the Calc 3 version of the second derivative test and apply it to a few different functions and see how we have a similar sort of procedure going on of find the critical points and then plug them into the second derivative test to see if they're maxes, mins, or saddle points. Take care. How are things going?
Oh, it's going pretty well, actually.
Your arm doing okay?
Yes. I mean, yeah,
Better?
it's on the mend. So,
Okay.
yeah, I'm still in a brace, but I can write is the main thing, and so I'm wondering if
Want to come by and start taking a bevy of retests?
yes. I don't think today would work, but maybe Wednesday, maybe try to do 2.
Okay, sure. Let's see. Wednesday. Are you available?
Office hours, yes. I should be free for at least part of the office hours, so I can come take.
Awesome.
Okay, perfect.
And so in that case, why don't you just send me an email between now and Wednesday saying which time you want to come by and which standards you'd like to retest,
Okay.
and I'll be ready for you.
Yeah, I think it would be about 5. I think is what it would be.
Five is one of them.
No. I'm saying I think in total, I think it would be about 5.
Oh, 5 retests even? That sounds about right.
Yeah, because
We're out for a couple of weeks there.
Yeah. Okay. So I guess start planning, taking a couple at a time. Okay.
Sure, sounds good. And, until you've made them all up, I'm not restricting you to once per week or anything.
Okay. Thank you. Thank you, Dr. Crystal.
No problem. Have a good rest of your day.
Okay.